Welcome to this explainer on the incredible world of chemical reactions. Today, we're exploring the absolute mastery of salt synthesis. Zooming down to the microscopic level, preparing a salt is really just the precise science of neutralizing an acid. We use this tightly controlled interaction to engineer one specific, totally predictable ionic compound. It's like a chemical puzzle. So, how do we make soluble salts? It depends entirely on whether your starting materials actually dissolve in water. If you're mixing an acid with a soluble alkali, you need a highly precise analytical technique called titration. We drop in special chemical indicators to pinpoint the exact molecular moment when the solution becomes perfectly neutral. But what if your starting solid, like a metal, base, or carbonate, doesn't dissolve? Then our whole approach shifts. We simply flood the acid with an excess of that solid. This ensures every single acidic molecule gets totally consumed. Next up, we physically separate this new mixture using a quick and easy process called filtration. The leftover solid gets trapped at the top as residue, while our dissolved salt flows right through as the filtrate. To finally get our pure salt, we evaporate the solvent. This leaves behind some truly beautiful geometric crystal structures. Now, predicting these exact chemical outcomes means we've got to master the fundamental, unbreakable rules of solubility. For example, all nitrates dissolve universally in water, along with your sodium, potassium, and ammonium salts, no exceptions. Chlorides also tend to be highly soluble. But watch out, lead and silver are the two big exceptions here. Sulfates, they can really dissolve pretty easily too, unless they're attached to heavy elements like barium, calcium, or lead. On the flip side, most carbonates and hydroxides are completely insoluble, ignoring those highly reactive alkali metals we just mentioned. Oh, and calcium hydroxide is a really cool chemical anomaly. It's actually only partially soluble in water. So, when we actually want an insoluble salt, we trigger a rapid, spectacular chemical event known as precipitation. Mixing two soluble solutions forces our target ions to bond instantly, literally crashing out of the liquid as solid matter. Interestingly, many salts naturally exist in a hydrated state. They chemically lock water molecules right inside their crystalline lattice. This hidden water is exactly what gives compounds like copper-2 sulfate and cobalt-2 chloride their vibrant, iconic structures. If you bake away that bonded water with intense heat, you're left with a completely dry, anhydrous skeleton. By mastering these dynamic links between solubility, physical state, and structure, we can quite literally engineer matter with absolute precision. As this predictive science scales globally, it makes you wonder, what impossible microscopic structures will we engineer next?